We will now talk about the next level of measure of sensitivity of price to interest rate, the convexity. Consider price as a function of interest rate, again, or as a function of force of interest. And for that price as a function of force of interest, take the second derivative of the price with respect to the force of interest divided by the price. This is termed the Macaulay convexity. Now, most finance books don't use that term, but it's very convenient to understand the relationship of everything, so we'll use it here. And if you have a security with deterministic discrete cash flows, the price is the present value of those individual cash flows A sub t. So we're using the same notation as before. And if we do the calculation of the Macaulay convexity, we see that that's equal to the weighted average squared time to maturity, whereas before the weight is the present value of a single payment divided by the total of the present value of all payments. So it's the weight assigned to the time t at which the payment A sub t is made. Because duration is minus the derivative divided by the price, and the price times duration, Macaulay duration, is equal to minus the derivative with respect to delta, and that we call this minus the derivative, we call this the monetary Macaulay duration of a security. We also see that the Macaulay convexity, which is equal to that second derivative, but the first derivative with a minus sign is equal to price times Macaulay duration, we can substitute that in the formula as you see here, and we arrive at a very interesting result that Macaulay convexity is equal to the square of Macaulay duration minus the derivative of Macaulay duration with respect to force of interest. The quantity appearing inside the formula, convexity minus the square of Macaulay duration, which we actually don't have exactly in the previous formula, but if you move one of the expressions to the other side, you get this. So the quantity written as m squared, which is minus the derivative of the Macaulay duration with respect to delta, and based on what we just did, is equal to convexity minus the square. Macaulay convexity minus the square of Macaulay duration is called the Macaulay m squared or Macaulay dispersion. Because the Macaulay duration is minus the derivative of respect to delta of the natural logarithm of the price, we also see from this that the Macaulay m squared is actually second derivative with respect to delta of the natural logarithm of the price as a function of delta. If we consider a security with discrete deterministic cash flows, denoted as always A sub t at time t, then the price is the sum of present values of those, and the Macaulay m squared is equal to, if we do the calculation, it turns out to be the weighted average of t minus Macaulay duration, the whole expression squared, where the weights are multiplied by those t minus the m squared, Macaulay duration, and the whole thing squared. And also, if we take the derivative of Macaulay m squared with respect to delta, that turns out to be equal to minus the weighted average of t minus Macaulay duration, that difference cubed. Now remember that we introduced that artificial probability distribution where the probability that big T was equal to little t was the weight W sub t, and with respect to that artificial probability distribution, Macaulay duration is the expected value of it. Now if you look at this, you clearly see that Macaulay M squared is the variance of that probability distribution, and then this derivative of Macaulay M squared with respect to delta turns out to be minus the third central moment of that probability distribution. The same concepts are developed for the relationship with respect to relationships of price with respect to the interest rates. The expression 1 over the price times the second derivative of the price with respect to the interest rate is called the convexity of a security, and then the second derivative of the natural logarithm of the price with respect to the interest rate, which is the same as minus the derivative of duration with respect to the interest rate, is called the M squared, or dispersion of a security. So what is the practical interpretation of all of this stuff that we're studying here, especially convexity? So we did note before that for a security with deterministic cash flows, the Macaulay duration is the weighted average time to maturity. And if we have those weights, we notice that Macaulay duration was the expected value of the probability distribution defined by those weights. But if we write things with those weights, you see that Macaulay convexity is just the second moment of this random variable, artificially defined, and Macaulay M squared is the variance of it. Now take a closer look. This second moment here is somewhat indirectly written in this, because I pointed out to you that, and the second formula that you see here says that Macaulay M squared is the variance. But Macaulay M squared is convexity, Macaulay convexity minus the square of the mean. And the variance is the second moment minus the square of the mean. That tells you that Macaulay M squared is, Macaulay dispersion is the second moment of that probability distribution. That means that Macaulay duration can be interpreted intuitively as the expected time until maturity of cash flows of a security. Macaulay M squared is a measure of dispersion of the cash flows of the said security, and Macaulay convexity is the sum of Macaulay M squared and the square of Macaulay duration. And dispersion, of course, gets bigger if the cash flows are more dispersed, if they're more spread out over time. Duration is bigger if the cash flows come later. And this tells you that convexity, which is the second moment, and the second moment can be written as the sum of the variance plus the square of the mean. Convexity gets bigger through both influences. You have more convexity if your cash flows are more dispersed over time, and also if they come later. Convexity is bigger if cash flows are spread all over very long variety of times, and if they are paid long term in the future. It kind of tells you why this is important in a study of insurance, because liabilities of life insurance companies have the greatest convexity of anything that is in existence. But you'll see very soon that convexity is a very desirable characteristic of financial instruments, provides protection from volatility of interest rates, from uncertainty of interest rates, reduces your sensitivity to changes in interest rates. Let's also note that by the chain rule, the derivative of the price with respect to the interest rate is equal to the derivative of delta with respect to the interest rate times the derivative of the price with respect to delta. And that implies that 1 over 1 plus I times dp over d delta is dp over di. And we've used this all the time. That gives us the relationship of Macaulay duration to duration. And it tells us that taking the derivative with respect to I is the same as taking the derivative with respect to delta and multiplying the result by 1 over 1 plus I. or taking a derivative with respect to delta is the same as taking a derivative with respect to I and multiplying the result by 1 plus I. So 1 over 1 plus I in one direction, 1 plus I in the other direction. Now if we do the second derivative, then using the chain rule a couple of times here, we obtain a formula that says that the second derivative with respect to price, with respect to the interest rate, of the price with respect to the interest rate, is minus 1 over 1 plus I squared times the derivative with respect to delta plus 1 over 1 plus I squared of the second derivative with respect to delta. And that actually implies that convexity is equal to 1 over 1 plus I squared times Macaulay duration plus 1 over 1 plus I squared times Macaulay convexity. A useful formula that you should be aware of, you should know. Now, we also have a measure of dispersion with respect to the interest rate, m squared, or dispersion. It's convexity minus the square of duration. And that's equal to the second derivative of natural logarithm of price with respect to the interest rate. And if we do all the calculation, we'll see that this is equal to 1 over 1 plus I times Macaulay m squared plus 1 over 1 plus I squared, 1 over 1 plus I squared in both cases, times Macaulay duration. Now, because Macaulay m squared is the variance of the random variable with the density that we artificially defined, it, and m squared, as a result, increase with dispersion of cash flows. Notice that. For a security with discrete deterministic cash flows, A sub t, its price is of course the present value of the cash flows, then its monetary or dollar convexity, a second derivative of price with respect to the interest rate, is 1 over 1 plus I squared times the sum of t times t plus 1, A sub t over 1 plus I to the t. Now remember, we only got t squared under Macaulay setup, but this is with respect to the interest rate. So we get this 1 over 1 plus I 1 over 1 plus I squared in front, and then t times t plus 1 inside. And convexity is equal to 1 over 1 plus I squared times the weighted average, not time squared, not time, but t times t plus 1. And that actually is, of course, the same as 1 over 1 plus I squared times Macaulay convexity plus 1 over 1 plus I squared times Macaulay duration, and that makes sense. That's consistent with what we had before. Now, some important practical observation. If we have a single payment at time t, then its Macaulay duration is t, and its Macaulay convexity is t squared. Its convexity is just t squared over 1 plus I squared plus t over 1 plus I squared. So it's t times t plus 1 over 1 plus I squared. Its Macaulay m squared is 0, and its m squared is t over 1 plus I squared. If you have a portfolio, then convexity of a portfolio is a weighted average convexity of individual pieces where the weights are proportional to market value of the pieces. In particular, if you have an instrument which is the sum of two other instruments, so the price is the sum of two prices or difference, it's the same way, then convexity is a weighted average of the convexities with plus if it's plus or minus if it's minus. Now, if the security that we are considering is not deterministic, meaning not fixed cash flows, but instead has embedded options, meaning that can be prepaid or can default, and these are options effectively, option to prepay, option to default, then the only practical calculation of convexity is an approximation for which we use the Taylor series expansion. We again write the Taylor series expansion of price as a function of interest rate, and we use the first two terms of it, the way you see here for P of I plus delta I and P of I minus delta I. We add the two, we get the formula that you see there, from which we get the formula for convexity, which is approximately equal to price at I minus delta I minus twice the current price at I plus price at I plus delta I divided by P of I times delta I squared. And that's more or less a standard approximation that you use for evaluating convexity of something that has interest-sensitive cash flows. Now we've come to a formula that will give you the magic of convexity. Based on that Taylor series expansion, we get this approximation that the change in price, which is the price at I plus delta I minus price at I, is approximately the first derivative times delta I plus half of the second derivative times delta I squared. This implies, if you divide everything by P, that delta P over P, so performance of the financial instrument, the change in price divided as a fraction of the price, what percentage of it you gain or lose, as a result of change in interest rate of delta I, is approximately equal to minus duration times the interest rate change plus 1/2 of the convexity times interest rate change squared. And of course, without convexity, it's just delta P over P is approximately equal to minus D times delta I, which I have given you before, maybe indirectly, but now you have it directly. But the formula involving convexity is very interesting because if delta I is negative, if rates fall, the first term, minus D times delta I, is positive. So you make money, typically, well, assuming duration is positive, which almost always is. So minus D times delta I is positive if delta I is negative. But so is the second term, assuming convexity is positive. Now, it is possible to construct some portfolios that have negative convexity, and eventually you'll study this. But for most instruments, it's positive. And what I'm trying to say is that the more convexity you have, the better. Well, then, of course, you want it positive. And this expression is positive if delta I is negative. But if delta I is positive, then, of course, minus D times delta I is negative. You lose money if rates increase. However, the second term is still positive because delta I squared is positive if convexity is positive. The more convexity you have, the lesser the impact of the change in interest rate. Although, because delta I squared is much smaller than delta I, the second term is typically smaller. You have a very simple exercise to illustrate a rather unusual portfolio, although it's not unusual for insurance companies. That's actually a situation that is pretty standard for insurance companies. Your company has a liability which calls for a single payment of $1,000 due exactly in 10 years, and it funds it with a 1-year zero coupon bond with a price of $200 and a 20-year zero coupon bond with a price of $800. Notice that the payment of $1,000 is way in the future, and the company has a $1,000 worth of assets right now, so the company is very well funded to make the payment. Current continuously compounded interest rate is 4% and the yield curve is flat, so interest rates for all maturities are the same. We'll discuss what that yield curve means very soon. Calculate the Macaulay duration and Macaulay convexity of your company's surplus. And surplus is defined as assets minus liabilities. And we're going to treat the company as a portfolio of positive investments, which are its assets, and negative investments, which are its liabilities. And we'll try to use the formulas that we learned for that case. I probably should comment that having an asset liability portfolio is, of course, standard for insurance companies, but the situation described here with a single liability, that's unusual, especially for life insurance companies. Life insurance companies typically have liabilities that are spread out over time, and their assets are less spread out. Here it's the assets that are more spread out. The company is in a pretty good position. So here is the solution of this story. The present value of the liability is that liability discounted at the continuously compounded, or force of interest, of continuous compounded rate of 4%, which is the same as force of interest of 4%, and comes out to be 670.32. The company's surplus is 1,000 minus that because they have 1,000 worth of assets. So it's 329.68. And we treat assets as positive investments and liabilities as negative investments. Macaulay duration of the surplus is the market value weighted average of Macaulay durations of individual pieces. And we have a 1-year bond worth 200, and it constitutes a fraction of the whole portfolio of 200 divided by the value of the asset liability portfolio, which is 329.68. So this weight times 1. The weight of the liabilities portion of the portfolio is minus 670.32 because that's a liability, so it's like a negative asset, divided by 329.68 times 10 because Macaulay duration of that liability is 10, plus 800 over 329.68 times 20 because a Macaulay duration of the asset, it's just a zero coupon bond, 20 years of a zero coupon bond is 20, and we end up with approximately 28.8061. Note that actually the Macaulay duration is bigger than any of the individual pieces. Note also that these weights that we have there in front of the times of payments, they add up to 1. That's just they are no longer less than 1 in terms of absolute value, but they add up to 1. And that's okay. You can still use the formula the same way. Macaulay convexity of an individual cash flow is the square of its time to payment. Macaulay convexity of a surplus is the weighted average of individual cash flows convexities, Macaulay convexities really. And that's, again, the weight times 1 squared plus the second weight, which is negative, times 10 squared, plus the third weight times 20 squared. Again, we end up with convexity which is bigger than any of the individual pieces, 767.9204. Duration and convexity can be calculated with respect to nominal interest rates such as I upper 2, I upper 3, and so on. And I upper 2 is the most natural choice because there are so many bonds that make semi-annual coupon payments in the U.S. In order to figure out what these are, and it's unlikely that you'll get this, but just want you to see that it's the same approach that would work. We know that 1 plus I upper m over m to the mth is 1 plus I, or e to the delta, so that di over d I upper m, the derivative of I with respect to I upper m is, well, it's m times 1 over m times 1 plus I upper m over m to the m minus 1. And that ends up being 1 plus I over 1 plus I upper m over m. And d delta over di upper m is d delta over di times di over di upper m, so it's 1 over 1 plus I upper m over m. Combining this, we get that the derivative of p with respect to I upper m is 1 plus I over 1 plus I upper m over m times the derivative of p with respect to I, and the derivative of p with respect to I upper m can be also written as 1 over 1 plus I upper m over m times the derivative of p with respect to delta. And based on this, we can derive the duration with respect to I upper m, as I wrote it as d upper m, 1 plus I over 1 plus I upper m over m times duration, or 1 over 1 plus I upper m over m times Macaulay duration. And the duration with respect to I upper m over m is m times d upper m. There's also convexity measure with respect to I upper m. For this, we would need to take the second derivative of a price with respect to I upper m, and we use the formulas that we developed. The result is actually quite simple. The convexity with respect to I upper m equals 1 over 1 plus I upper m over m squared times convexity, with Macaulay convexity, plus 1 over 1 plus I upper m over m squared times 1 over m times Macaulay duration. But we can also solve this entire story or problem by switching to effective interest rate over a shorter period of time. And duration is expressed in units of time. The unit of time is that one that is used for the period of time over which the interest rate is given. So if you have an annual interest rate but is not effective, that's like compounded, say, m times a year, you can switch to 1/mth of a year, figure out the effective interest rate there, figure out the duration, and then if you, for example, get the duration to be, let's say, m equals 2, and the duration is 6 half years, then obviously that means 3 years. Notice, however, for convexity, the unit is a year squared, if time is in years, so you need to ask yourself how many half years squared are in a year squared, and the answer is 2 times 2, or 4. And because there are 4 quarters in the year, there are 16 quarters squared in a year squared, so you need to be careful with that. But that's a reasonable approach as well to figuring out convexity or duration with respect to nominal interest rates.